Good morning and welcome back to whoever may watch this video. It occurred to me, I never completed my intended series on an interface theory of reality. I did part one. I had multiple videos in mind and I just haven't got around to it. So I figured this morning I would actually try to go back and sort of fill in the gaps of the areas I hadn't discussed. I'm not drinking whiskey or smoking a cigar. It's too early in the day for that. But I did wear a more festive shirt, so hopefully that makes it fun. I'm also trying to take advantage of some of this morning light, which is very nice. But if you watched the last video on interface theory, basically we're looking at the work of Donald Hoffman. I recommend this book, and he sort of lays out what an interface theory actually is and what it looks like based off of evolutionary fitness payoffs. So read that book or just watch the video that I made, and that kind of is where we started. Where we're getting to and what we started to get into at the end of that last video was quantum mechanics and quantum particles. So probably the best source on this that I've come across is this is sort of the standard. It's the QED, The Strange Theory of Light and Matter by Richard Feynman. Okay, and in this little document that Feynman presented a long time ago, at the early onset of sort of discoveries about quantum physics and quantum mechanics, he does what's known as the slit experiment, which is basically a pretty simple experiment using a piece of slitted paper and a photon particle emitter. Okay, I'm going to show you a couple slides here of the experiment so you can kind of get a visual idea of what those slides are showing. And then I'm going to kind of also do my own little sort of generic version of the experiment to show you sort of what the expectation would be. And then we'll get to why they did this experiment and why it's so revolutionary and important. So here's our slit experiment. We have this piece of paper here, and you can see there's 3 different slits, and behind it we just have a white board, so that's very visible. And I just have a little laser pointer. Okay, and as I'm going to do is just hit the laser, and as I shine the laser through, so if it's here, there's nothing on the white panel, you can see because it's being blocked by the paper. But as I move into the slit, you can see there's the beam on the white box. Okay, and we can do that over here, there, good. And then we can do it over here, good. Anywhere there's a slit, there is the light on the back. This is, of course, what one would expect to see in an experiment like this. But when they started doing this on quantum particles, they found something very strange. Here's a quick diagram of the actual slit experiment. You can see on the left there is a photon emitter that's sending the photon particle through the slits. And then on the back side, you can see the interference pattern of light that's being recorded as a wave. If you look at the bottom there, there's a sort of green light color, which is a visual example of the white or the light wave that's being recorded on the back sheet there. Electromagnetic spectrum also exists as a wave, and here you can see a comparison of that electromagnetic spectrum in relationship to color vibrations, which shows the relationship between those 2 waves. Okay, so if you have any background just sort of exploring into the field of quantum mechanics for whatever purpose, you've probably come across this experiment before, because it is a sort of common, sort of foundational idea. And basically what it's establishing is the wave-particle duality of light, okay? And the fact that while light, photon particles seem to exist as particles when they're being observed by us, they actually are waves. So it's 2 different things at once. And the question that became the central component of all this, the central question of all this was, well, how does that work? How can you have something that's 2 different things at the same time, and that perceptual analysis of that thing actually seems to adjust or change the results, okay? Meaning that the observer, we as the observer observing the photon particles, are actually what makes it appear as a particle versus a wave. And that's going to be something we get into in the last section, part 4, or what I'll call part 4, when we start talking about some of Walter Russell's claims. Walter Russell, by the way, is not an actual scientist. He's a very interesting guy and a background in the arts, but I want to talk about him just because I do think he makes some points. And then, of course, we'll get into Carl Prembram's holonomic brain theory. But I want to move on to this guy. Okay, so this is a man by the name of David Bohm. I don't know if you can read that's probably not going to focus. It's called Wholeness in the Implicate Order. Okay, all right, what it says? Yeah. So this book is interesting. It's got a lot of decent material, and really that's the last section, though, of this book that I find to be the most helpful, and is also the one that's often referred to the most frequently when it comes to this discussion of sort of an interface theory of reality. And it's called the fish tank experiment. In this book, it comes in 237, and you'll kind of see it down here, what happened. Now, Bohm actually was a student of Einstein's, and he was a leading physicist in the field. He was highly touted and was kind of expected to be, sort of the next Einstein. But they kind of had a falling out because Bohm came to a different conclusion than Einstein, and it all had to do with space and time. If you know anything about Einstein's theory of relativity, it's a theory that's grounded in space and time. That's where Einstein begins his whole process. He says, we can agree that both space and time exist, but what is their relationship, okay? So every scientist, every experiment has to have a foundational idea that it's working from. And for Einstein, the idea was, well, space and time are foundational, so we just need to understand space and time better. And he believed that if we had a better, more robust understanding of space and time, we would be able to explain not only gravity, which he was able to articulate, but this theory of relativity would actually explain more things. But the further science has gone down the road of quantum mechanics and quantum physics, the further they're getting away from finding what's called the unified field theory, right? Which is the ability to link our sort of standard ideas of physics, Newtonian physics, Einsteinian physics, with quantum physics, because quantum physics, again, doesn't behave like normal objects within space. So the thing that Bohm had proposed, which is why he and Einstein had a falling out, and which is why, for a long time we didn't hear about this guy, but now he's becoming more and more in vogue, is he proposed that space and time were not foundational. And that was actually based off studies he was doing in the realm of quantum physics versus standard physics. And the experiment that he did involved two fish tanks. I kind of did like a silly version of my own experiment using a Lego shark, which I'll show you here just to kind of give you a rough idea. But I'm going to explain it first so you kind of know what I'm trying to say. But essentially what happened is they set up this experiment and they had a fish tank. I say two fish tanks. It was actually, truthfully, just one. And this is sort of the trick of physics and perception. So there's a central fish tank, and they put a fish, or maybe multiple fish, I don't remember, in this tank. And then they had actually two different cameras set up. So one was facing, one side of the fish tank, and the other was coming in facing the other side of the fish tank, okay? But each camera couldn't see the other camera. All it could see was the fish in the tank. And then they ran those cameras out into a observatory room, which was a different room, separate off from where the experiment was, and they connected each feed as a live feed to a television, okay? And so there were two televisions in the observational room. And what they found was that while people were observing these fish tanks, and so, the fish moving in the tanks, they were unable to identify the fact that it was the same fish in the same fish tank. And that's because the angle was different. So even though they were actually looking at the same thing, because they were looking at it from different angles, it moved in different ways. And they could sometimes maybe see that there was a strange correlation, right? That they're kind of moving all the same, but they couldn't really put it together. It wasn't until the people in the experiment were shown the back room and allowed to see that they were actually looking at a single fish tank that they had an understanding of what was actually taking place. So this was a situation where they were looking at a two-dimensional thing, right, a TV, and watching the fish in two dimensions, when in fact, because in the three-dimensional space, it was being filmed from two different angles, when they saw that, they could see how each of those different two-dimensional representations were actually the same thing. And what Bohm realized in this process was this was not unlike the way particles behave. And that in the sense that there seems to be this sort of quantum entanglement where there's these connections between particles and they seem to be working together in unison in some ways that we don't understand. And that's why he proposed there has to be some type of other dimensional plane that exists outside of this space that does make sense out of how these particles move and behave, but that we can't see it because essentially we don't have access to that back room, okay? So it's a really interesting experiment. You can read about it yourself in here or explore it online. I'm sure there's some great tutorials on there. But all of this gets back to this idea that we talked about in this book about the case against reality, which is, again, this idea that reality seems to be bigger and more robust than we tend to think. And we started to see signs of that early on in the realm of quantum physics. But the further we go down that path, it seems like we have to rethink what it means to talk about reality itself, okay? Now, I'm going to show you my little experiment with the fish, so hold on, check this out. Hopefully it makes sense. So here, hold on, watch that. Okay, here's my little silly experiment of a fish. Not perfect, and my timing was a bit off, but you can kind of see how from different angles the fish could appear as a different fish if someone didn't realize they were actually looking at the same fish being filmed from different perspectives. If you hold on here, I'll actually show you a look at the original experiment that was conducted by Bohm. There you go. So that gives you a better visual example. You see the camera filming the fish from each side, and then the separate television screens that the viewer would have been able to see. Okay, so not perfect because I was just doing it with my hand. I did it very quickly. But at least hopefully you get the idea of how it looks different, and there seems to be maybe some relation, but not. So yeah, it just shows how we perceive reality is based off perspective. And that's where we're going to get into this guy. So that's going to be part 4, the final part. This is one video, but I'm basically covering two forms of the video. So part 2 would be essentially just the wave-particle duality of light. And part 3, I guess, would be the fish experiment and sort of thinking in other dimensional planes outside of our common 3-dimensional planes. Okay, so now we're going to look at brain perception. So that'll take us to part 4. Okay, we got a change of scenery here. I'm in the bedroom because I wanted to be in front of the keyboard here. Now I'm not a music expert by any stretch of the imagination. But if you are a music person and you have played the piano, if I hit this note right here, you're probably going to know that's middle C. But you're probably also going to know that there's actually multiple C's on a piano. So up here, we could come up here or go down. And those are all C's. And then, of course, from there, there's a scale of our various notes. So C, D, E, F, G, and then back to A. Okay? Normal scales on a piano. Now, the reason why I'm showing this example is because in order to create these tones on a traditional piano, this is actually a digital piano, so it's maybe not the best example. If you've ever opened up the back of the piano and look, you see all the piano strings. That's why it's a stringed instrument. It's because all of the tones and notes are coming from the vibration of a string. Okay, and the way that a piano is tuned traditionally is you have to tune that string to a specific note. And as long as that piano is tuned correctly, every time you hit middle C, you're going to get a C tone. And every time you hit E, you're going to get an E tone. Okay, and that's how the piano works. And then from there, you can actually be Beethoven and make some music. The same thing applies to a guitar. So let's look at a guitar because it actually has strings that are visible to the eye. Okay, I'm back with my guitar. I don't know how well I'll be able to fit it in the video here, but obviously a guitar has strings on, and each string is also tuned to a specific note. Mine might be a little bit out of tune because it's been a while since I played it. But essentially, as you hold down the string, you can lower it and change the tone. Pretty self-explanatory. This is how we create music. And of course, there's things like bar chords where you can bar off all the strings to make different notes, or they have even things like this you've probably seen, which is called a capo. And that allows you also to just shorten the strings where you want to shorten them by putting pressure on the fret, which then changes the tone. Okay? Pretty well makes sense, right? This is how tuning itself works. Well, this is a really good example for things that you may not think about. And that's going to take us back to Prembram and his holonomic brain theory. So, now we're back, and we're going to talk about this guy, okay? Carl Prembran, his Brain and Perception. Now, this book is not as accessible. It's pretty academic. These are some lectures he gave that he sort of outlines his theory, which has come to be known as the holonomic brain theory. But these are presented to other scientists in the field. It's actually a lecture series that he gave over a period of time. But essentially what he lays out is a new finding that he found as one of the sort of figures at the forefront of brain science and perception. And that was the discovery and at least understanding that came with things known as dendrites, okay, which are these tiny little finger-like filaments that are found on brain neurons, okay? So if we think of the way that we traditionally think of how the brain works, how we used to think the brain worked, we tended to think that our senses, and in this case like our eyes, our perceptual field, our eyes, are taking in information from the surrounding world. And that information is then going in and it's being essentially mapped and interpreted in our neurons of our brain. And then from there, it's sending out information that comes, to our brain that sort of shows us what the world looks like. And this is everything from taking in light and shadows and colors and sounds and things like this, okay? A good example of this would be if you think of how a traditional camera works, right? Where if you know anything about a camera, you have a lens at the front, which is capturing the light from the outside. One thing that makes a camera really good is the quality of the lens, right? And you can actually get different types of lenses. But in old traditional cameras, they were what was called single lens refraction cameras, okay? Which means that when the light came into the camera, there was a mirror. And if you look, you can usually see the mirror inside. And the mirror is capturing the image that's coming in the lens, and then it's shooting it up and it's bouncing it off prisms and then sending it back to the viewfinder so that you know what you're taking a picture of. And then it's printing that onto the photo film through the use of shadows and light and depth, which is why initially, if you think of old cameras, it was always black and white because it could just pick up the tones of light versus dark shadows. But as the technology advanced, they were actually able to incorporate the capturing of color, which is, of course, also a vibration of light, which we're going to come back to. So the idea was sort of that our brains were like cameras, okay? And that we're just sort of taking it in and it's sort of like almost like a single lens refraction, just going up into our head, and then we're sort of capturing it just like we would in a viewfinder, and we sort of have this perception of the world. But that turns out that's not actually correct. After we've moved forward technologically in the realm of science, a couple interesting inventions emerged. So one of them was actually lasers, okay? I don't know if you can see this on here. I'm going to put it on my hand, okay? And a laser is basically just using light in the form of interference patterns, okay? But it's manipulating those interference patterns in a very specific way, so you have a very, very, strong beam of light that doesn't break apart or dissipate in the way we would think light normally does, okay? So if you think of like a flashlight and you turn a flashlight on, the beam would be very large and wide, whereas with a laser, it's gonna be very tight. And it's gonna usually have a very specific color, okay? The best way to think about interference patterns is, firstly, keep in mind what we learned about wave-particle duality of light, and that light is actually a wave, not simply a particle. And if you think of the way an ocean works, right, and there's waves in the ocean, there's going to be times when those waves collide and cause conflict, but there's going to be times when those waves, they're moving the same way, they join together and actually make a bigger wave, right? And this is how you get really large waves. For a person who grew up surfing, that's what surfers do. They try to watch the wave patterns and see when they're going to collect in the right way to create the right wave for them to catch to surf. So it's the same idea with light. So when they invented lasers, they essentially were looking at the various interference patterns of different colors of light, and then they were trying to find those interference patterns that worked collectively together to make the beam of light more robust or tighter and longer so it can shoot very long distances to create lasers, okay? Which a laser can go really, really far away. If you've ever seen someone, playing around with a laser, they can shoot it across a room and it still maintains its integrity. You can still see the little dot, okay? Whereas a flashlight doesn't quite accomplish that, okay? Another invention that came along was also holographic images, okay, which was a development that came by way of lasers, actually. Someone figured out, I don't know who, that if you used lasers which again are more sort of robust or tighter, I guess is the way to describe it, a tighter beam of light. It actually contains more information and can capture more information as it comes across objects. So the way that they actually created holograms, if you've ever seen a hologram, is they would take an object. So I'm going to just see if here's a bottle, okay? We're going to just turn that like that, okay? And then what they would do is they would set a series of mirrors around the object, and then they would put, so imagine where this camera is that I'm pointing at, they would put that, would be where the actual holographic film would be. And by bouncing the laser off various mirrors, it would shoot. If you've ever seen like a spy movie and there's all the lasers going around, the guy in the museum trying to rob the item. Okay, imagine that. Imagine this is surrounded by all these lasers, and all these lasers are being redirected with the mirrors back to the holographic film. Those lasers were actually capturing the object from all different types of angles and vibrations. And then when it's recorded back onto the holographic film, and you reapply light, because if you've ever seen a hologram, it just kind of looks blurry, right? Unlike a normal photo that you would look at where you just have an image. But when you reintroduce light, the actual image comes to life and it emerges off of the film. And actually, as you move, the image moves as well, okay? And that's because all of that information is contained in the various laser beams that moved around the object, and all of that is also being retained in the holographic film, okay? So all of this is just different ways in which waves of light can be used to manipulate and shape information, okay? So that brings us back to this idea of brain perception with Prembram. What he found from his studies is these little filament-like dendrites that are on our neurons are actually tuning our perceptual data, okay? Meaning that before that information even gets to our brain, it's being tuned first. Much like when we hit a key on the piano and it produces a middle C, or we hit a string on a guitar and it plays an E flat or whatever you want to play. Those are already tuned to that. Now, there's an infinite number of notes you could do on a string, right? And you can have thicker strings, thinner strings. You can, make them longer or shorter. All of those are going to create specific tones. But on a guitar, you want to have specific tones, so you tune the guitar to that. Same with a piano. In a piano string, there's an infinite number of sounds you could make. But because you're trying to create a specific tone, each note is tuned to that tone. Okay? Well, what Prembram was proposing is that our brains actually take in the perceptual world and then tune it to a certain perceptual understanding. Meaning that what we are actually seeing in the perceptual world is not the perceptual world as it appears, but rather as the perceptual world has been tuned by our brains to understand. Okay? Now, all of this gets back to all of these theories, okay? Bohm, with this idea that there's other dimensional planes outside those that we experience. Same with Hoffman, who proposes that we are conscious, but our interface, okay, if we think about perceptual brain theory, you could say that the dendrites of our brain are tuning our perceptual reality to a space-time perception, still grounded in consciousness, but that's only understood through the lens of space and time, which is exactly what Hoffman proposes. The quantum world, however, seems to behave and act differently because in all probability, based off current science, it exists in a different dimensional plane that we can't fully understand, not unlike the fish experiment, where you had fish being filmed from different angles. And even though it was the same tank, because it was from a different angle or a different dimensional space, it appears differently, okay? But it's all connected and unified in one strange way. When I started this whole thing, I talked about Terrence Howard, who was on the Joe Rogan show, and he was talking about some interesting ideas. He's particularly talking about this guy, Walter Russell. Okay. Now, Russell is an artist, more so than a scientist, although he wrote a lot of books, and he has a very strong following. But the thing that Howard pointed out that was really interesting was the way that Russell explains the periodic table. okay? And the idea is, rather than setting up the periodic table just numerically in order, he created it like a wave structure, moving each particle or periodic, each thing of the periodic table, each element, periodic element, following that line and showing that it exists on a different vibratory wave, okay? Now that may be hard to understand, but if you think about another example, this may help, okay? Water. Water is ubiquitous on Earth. It's a huge part of us. It's a huge part of our environment. But within our experience of reality here on Earth, we experience water in all three states, okay? We can experience as a liquid, which is how it's most commonly found, right, in its sort of normal state. But if we put it in extreme temperatures, it turns to ice, right? If you heat it up, it turns to steam. All of that has to do with vibration, right? When you freeze something and it gets colder, the particles come together and they vibrate slower. And so the object actually gets harder and it becomes more solid like matter, right? When you warm it up, it turns to water, which means it's more fluid, right? And then when you heat it up to a certain extent, it becomes steam and it actually turns into a gas. And all of that just has to do with particles vibrating, okay? And how they're vibrating based off temperature, okay? So what Russell is essentially trying to highlight in his wave-like periodic table is that all elements within our world are just vibrating things, and the way that they vibrate differs based off of what they are. And the things that we look at as being solids versus liquids versus gas just have a relationship to how they vibrate and exist within our world, okay? So all of reality, as we perceive it, whether solid, liquid, or gas, is really just about vibratory patterns, okay? And that if you change the vibratory patterns in, say, a different space and time or a different dimensional plane altogether, those things would fundamentally change, okay? Now, if you take that into correlation with Prembram's theory of brain perception, and think about the way that our brain and these dendrite cells are essentially tuning perception, well, now we really have an interesting portrayal or articulation, potentially, of an interface theory of reality, or a holonomic brain theory of reality, where our brains are experiencing a reality that's not real in the way that we thought. All of this comes down to essentially this idea of scientific reductionism, right? As science emerged as sort of the predominant modality of thinking and understanding, we operated under this thought process that the more we reduce things down to their most fundamental base, the better our understanding of things will be. And eventually we'll get to these sort of foundational building blocks of reality itself. What is actually happening, we're finding out, is the opposite. And that the further we go, the less there is. It's nothing. It's just empty space. It's just vibrating particles in empty space, okay? Which suggests that reality as we experience it is really the product of our consciousness within space and time tuning, okay, the perceptual world to be a reality that we experience day to day. But that there's actually much more going on at some other dimensional plane that we don't even realize. I hope that all makes sense. I kind of covered a lot in a short amount of time, but my videos do have a tendency to drag on. And of course, I have given you the references, so if you want to go back and look into some of this stuff yourself, check it out. I'll throw some images up here at the end from Prembram's work, just so you can get a visual idea about that. Hopefully you found that interesting. I kind of lumped all three of my videos together. So part one has a full video on it, and that's really looking in depth at, I don't have the book here, or do I? Oh yeah, looking at Hoffman's book. And then part 2 and 3, looking at Feynman and Bohm and their physics sides of things, and then this being sort of part 4 with brain perception, and then bringing it back to this sort of ideas and thoughts by Russell. All right, check out these slides and have a great day. Here's a quick look at a single lens refracting camera. You can see the camera in the mirror and how basically the light comes in and then reflects off the mirror and then goes up and reflects off another mirror or prism to the viewfinder. Here's a quick look at neurons in dendrite cells. If you look at the number 1, look carefully there, those are the dendrites. These are these tiny finger-like filaments that come off the neuron that vibrate and essentially tune or tone our perceptual data. Here's a traditional look at the periodic table as you saw in your chemistry books in high school. This I like to call like the Crayola crayon color box of, of periodic tables, and that being a reference to how crayons are organized in a box. So what Walter Russell proposed was to draw the periodic table this way, which captures it in a wave form so that it gives you a different perceptual understanding of how these different elements vary with different vibratory patterns. This is a much more robust idea and to me looks a little bit more like our variations of the color wheel, which I think gives you a better understanding of how colors relate versus then the way they're tended to be looked at, for example, in a Crayola crayon box. And lastly, here's another look at it where they're using the color wheel to also organize those various elements based off their wave formation. It's sort of a different way of looking at Russell's model, but I think something that's more visually helpful, but also maybe helps to show the correlation between perceptions, in this case, the perception of color, and as it relates to different vibratory wave patterns.